Hello everyone. In this session we will discuss about the instrumentation amplifier. So name itself, it is an amplifier. You know the amplifier is which converts the small magnitude signal into the high magnitude signal. What is the instrumentation? Instrument is nothing but which is useful to measure the quantity simply. So simply we can give small definition. The meaning of instrument, the instrument is nothing but to measure quantity. It may be any quantity. To measure any quantity. That means to measure the current, we are using ammeter as instrument. To measure the voltage, we are using voltmeter as the instrumentation. So how the op-amp is used as instrumentation amplifier, in this topic we will discuss in this session. Okay, look at here. It is also a kind of differential amplifier. This is nothing but a differential amplifier, but this differential amplifier is modified. So we did some modifications, but it has very high gain. So gain must be very high gain. Generally differential amplifier has a moderate gain. Here we can improve into the very high gain and very high CMRR. CMRR is also very high, and with the ZA means input impedance. So we have some differences between the differential amplifier and instrumentation amplifier. That is, it has very high gain and very high CMRR and very high input impedance. It is used in industrial application and test and measurements. It is used in industrial application. Generally it is used because to measure the current and voltages, it is an application generally, and tested measurements. So in the measurements also it is useful. Okay, this is the difference between the differential amplifier and the instrumentation amplifier. Differential amplifier, you know everything about differential amplifier, but instrumentation amplifier has very high gain, very high CMRR and input impedance. Instrumentation amplifier preferred over differential amplifier. Generally instrumentation amplifier is preferred than the differential amplifier because common mode signal and resistance matching also required. That means the common mode signal is generally available in the differential amplifier, but that common mode signal must be removed, must be eliminated. Then we are getting perfect instrument, otherwise we will not get. And with that we require resistance matching also. Resistance matching also important thing. So the resistance, we will discuss about resistance matching and resistance matching in continuation part. Okay, here he will give the explanation here. The common mode signal also amplified in differential amplifier. Generally, what is the problem with the common mode signal? Common mode signal is nothing but the noise. Noise is also amplified. So in the differential amplifier, when we are using as instrument, the problem is we will get error because common mode signal also amplified. To avoid this, resistance matching is used. So to avoid this problem, we are going to use the resistance matching. Okay, this is about the instrumentation amplifier. So this is the construction of the instrumentation amplifier. Here we have two inputs here, VA and VB, and here VA is given to non-inverting terminal, VB also giving to the non-inverting terminal, two operation amplifiers, and we have the another operational amplifier is there. Okay, here we have three resistance connected. So from the output point we have R5 is there, and from the output of the VA we have R6 is there. Between R5 and R6 we have RG resistance is there. Okay, and if you consider VB will give the output is VB dash, and VA will give the output of VA dash. Okay, so completely it will generate the output. Okay, so here we will discuss the operation here. First, only differential signal is amplified, common mode signal is not amplified here. So generally instrumentation amplifier is fabricated in IC. Generally it is fabricated by the integrated circuit except RG. So generally except RG is not available, but in the circuit RG is available. Due to the fabrication, internal resistance are matched. Due to this, we have the internal resistance, those will be matched. So that will be, we will discuss here. We have internal resistance, those are R5, R6 is there, and R4, R3, R2, R1. These are the internal resistances. The internal resistance should be matched. That means the matching is nothing but here the R5 will be equal to the R6. That is, this resistance must be equal to this resistance, and the ratio of R4 by R3 equal to ratio of R2 by R1. So that is, we will take the R4 by R3 equal to R2 by R1. You should maintain some ratio. So by that ratio we will get the output is like this. The output is generally, if you find out the output voltage we have directly, by doing the calculation we will directly get the formula, that is 2 into R5 by R6 into R2 by R1 into VA minus VB. So this is the output formula. This is the output voltage of the instrumentation amplifier. Here, so if you substitute these things, and we can write output for another formula. Look at here, we have two inputs, VA dash and the VB dash are the two inputs. If you consider these two inputs, what is VA dash? Here input is VA, when it is converted then the output is become the VA dash. If the input is VB, then it will convert into the VB dash. So by using that we can write the output equation also. That output equation equaled like this, that is R2 by R1 VA dash minus VB dash, and here we can modify like this also, that is we can use R4 by R3 equal to R2 by R1. So if you modify this we will get the equation also. So generally if you consider the current flowing in this RG resistance, for example the current flowing in the RG resistance is IG. So current flowing in this G resistance is IG. Then we can write the IG value is like this. So the IG is nothing but the drop VB minus VA by RG. So just take that value, the IG equal to VA minus VB by RG. One thing. Next, we can write VB dash minus VA dash also. Here we have the VB dash, this is also the VB dash, and we will get the VA dash also. Now we will write the drop between these 2 points. Then the drop between the 2 points is like this, that is VB dash minus VA dash value is like this. That is, so drop between all these resistance, the current will IG into R5, IG into RG, IG into R6. Then it will give the drop between the VB dash and the VA dash. So just write it, VB dash minus VA dash is equal IG into R5 plus R4 plus RG, R5 plus R4 plus RG. This is also the one equation. From this you know that R4 equal to R5. So R5 equal to, so this is R4, R5 equal to, so finally we can write not R4, that is R6 actually. This is the R6. Okay. Then we can write R5 value, R6 value, both are matched. So by this it will be modified like this, IG equal to 2 into R5 plus RG. Okay. You know the IG value, just substitute this IG value in this equation. The equation will be modified like this, that is VB dash minus VA dash is equal. So by substituting this we will directly get VA minus VB by RG into 2R5 plus RG. This is 2R5 plus RG. So by modifying this, finally we will get VB dash minus, so it is VB dash minus VA dash. We can modify like this: VA dash minus VB dash value equal to VB minus VA. So then it become 1 plus 2R5 by RG. 2R5 by RG. So finally we can write this, we will getting the VA dash minus VB dash value, but you know that the output V naught value is here we have the formula. Substitute in this formula. We have two formulas, this formula and this formula. In this formula, just output equaled V naught equal R2 by R1 VA dash minus VB dash. R2 by R1, that is VA dash minus VB dash. VA dash minus VB dash. Assume some equation 1. Substitute equation 1 in below equation. So if you substitute this, we will get the formula is like this, that is V naught equal to R2 by R1. VA dash minus VB dash is nothing but VB minus VA into 1 plus 2R5 by RG. 2R5 by RG. Okay? Yeah. So VA minus VB. Here we have VA dash minus VB dash equal to, so we are not modify this, just VA minus VB. So this is also we will get VA minus VB. So we will get that equation. So this is about the final output. The final output of the instrumentation amplifier. Okay. So by doing this, we will improve this. So this is the final output equation, that is the output equal to R2 by R1 and VA minus VB, that is VA minus VB. So this is VA and this is VB. Okay, yes, VA minus VB and 1 plus 2R5 by RG. So 1 plus 2R5 by RG. Okay, so in this way we can improve the CMRR value, and with that common mode signal will also be decreased. This output voltage CMRR will be increased and common mode signal will be removed, delayed. Common mode signal is removed or eliminated. So that's why common mode signal is eliminated. That's why this instrumentation amplifier is very much applicable. Okay. So by using the op amps, this is the construction of the instrumentation amplifier. This is the output voltage of the instrumentation amplifier. Okay. Next is analog to digital converter. So here the operational amplifier is very much useful to converting from the analog signal into the digital signal. So analog signal into the digital signal. Here the analog signal may be like this. Analog signal means the continuous, the magnitude have continuous waveform. Maybe this may be the analog signal. So when we are giving to the ADC, analog to digital converter, the signal can be modified like this. So it is maybe 0 1 0 1 0 0 and 1, like that. So we have only zeros and 1, that is the digital signal. Where the output appears in the form of zeros and ones, that is the digital signal. Analog signal is the magnitude is continuous with respect to the time, is nothing but the analog signal. The device which is used for converting analog signal into the digital signal is known as the analog to digital converter. Here generally we have more number of analog to digital converters. We have such types generally mentioned here. The first is successive approximation type ADC. Second, flash parallel type ADC. ADC means analog to digital converter. Third, counter type ADC. Fourth, sigma delta type ADC. Fifth, dual slope integrated type ADC. So here we have more number of ADCs. Just I will take the reference is the digital slope or integrating type ADC. So here this is the dual slope or integrating type ADC. Integrating type means here we are using the integrator circuit. You know the integrator circuit, it has the capacitor is connected as feedback and the resistor is connected like this. And after getting so we are using two things, one is the input and another one is the reference. So input is, you know, the input is nothing but the analog signal, that means must be it may be the sinusoidal or it may be the square waveform, it may be the rectangle, triangle like this, it must be the analog signal. And we should use some reference signal. We have a condition between the input voltage and the reference signal, that is input voltage reference must be in opposite polarity. That means if the input voltage is positive polarity, it should give the reference is the must and should be the negative polarity, otherwise it will not work. And so to operate the V input we have the control circuit here. The control circuit will decide which the input it should take. It should take the input value or it should take the reference value. That is controlled by here we have the control circuit here. So for example we are giving some input, the input will be flow through the R and C combination. R is the input resistance, C is the capacitor, so it is nothing but the integrator circuit. After that it will be given to the again the 1 ohm, then we will get the output, some output here. Wherever we should give some clock signal, wherever we should give the clock signal, here we should use some NAND gate. It is nothing but the AND gate, sorry. What is the application of the AND gate? When two inputs are 1, then output is 1. Otherwise, all conditions it is 0. Otherwise 0. So by that principle, if the output we are getting the 1 here, then automatically the counter will be show here 1. And if it has the 4 digits, then it will show it is a 4 digital outputs. It will start from 0002 and it will end with 4 ones. And for every input it will count the input. That's why it is called the n bit counter. N means 1 2 3 4. Here n value is 4. If 3 is there, n value is the 3. Okay, this is the digital output, then it will get the output. So this is the working of the dual slope integrated type. So in this we should write some point, that is when we should have some values, that is when V0 is greater than 0, that means we have V0 is there, the V0 value is like this. So here this point, this V output is V0. When V0 is greater than 0, then automatically it will give the output value must be 1. Whenever V0 is greater than 0, that must be 1. And when the V0 is less than 0, the output value is the 0. So look at here. This is the V0 point. If it is greater than 0, the output value is 1. Less than 0, the output value is the 0. We will get that. And here after getting 0 or 1 here, maybe 0 or 1 here, we will get 0 or 1 here. It match with the clock signal. It match with the clock signal. Okay. Okay. So then both inputs are 1, the output will be given, otherwise output will be 0. So generally clock signal representation is like this. The clock is like this. One pulse, this is the on time, and this is the off time. This is the clock signal. And here when we can write the another condition, when the output is greater than 0, when V0 is greater than 0, we will get the output is 1. And then clock passes, and the clock will get clock passing to n bit counter, then automatically it will enter into the n bit counter here itself. Look at here, when both inputs are 1, then clock passes and it will get the n bit counter. Okay, so we already discussed, if the 3 bit counter, it counts from, if it is a 3 bit counter, 3 bits are available, then it will count 3 zeros to and 3 ones. If it is a 4 bit counter, it will count 4 zeros to and 4 ones. Okay, right. But in order to count complete counting starting from 0002 to complete all ones, it will take 2 power n minus 1 into t cycles, t clock cycles. It will take, the time value is this much of time. The time must be 2 power n minus 1 into t. T is the clock time period. T is the clock time period here. So n is the, t is the clock time period, and here n is the number of bits. Generally it is the number of bits that will depends on the clock. To complete from 3 zeros to 3 ones, that means here 000, 001, 010, from that. So to complete from this point to this point, it will take this time. Okay, yes. And so this is for a complete counter, but total time will be represented like this. The total time is, total time t equal t1 for process plus 2 power n minus 1 into t. So t1 is the process time. Actually, to counter that, process time means, for example, it will change from 000 to 001. It should process, or it should pass through the amplifiers, and that is called the process time. So that process time also same as that value. That means we can write 2 power n minus 1 into t plus again 2 power n minus 1 into t. So by common this, we will get 2 times of 2 power n minus 1 into t. So finally we will get the total time period equal to 2 power n plus 1 into t. Okay, so here you know that the total time you know that. So remove this t, this is the total time, because you will confuse, you will get some confusion. That is, this is the total time only. So you know that t is the time period of the clock and n is the number of bits. So generally it will take this much amount of time to complete the process. So this is the problem with disadvantage. The disadvantage is it is very slow. It is very slow. That means it will take more time to process. It will take more time for conversion. Conversion means to convert analog signal into the digital signal. But it has a good advantage, that is it is very accurate device compared with the all the devices. Okay, it is accuracy compare in all ADCs. So in accuracy point of view, this is very much useful, but the disadvantage is it is very slow. It will take more time to for conversion. Okay, so this is about the analog to digital converter by using the operational amplifier. Okay, so I hope all of you understand the session. Thank you.